In the last lecture, we have discussed this example where we found the Fourier series of f of x equal to x squared for 0 that's less than x and less than or equal to 2. So just a quick review, what we did was we first made the function periodic by extending the range of interest to -2 to 2 in such a way that f of x is equal to f of negative x. And we ended up with an even function with period of 4. This is again here your x squared function, and we extended it to the range from -2 up to 2. And we have this period here, which is equal to 4. And we noted that since we have made the specified function even in x by extending the range, all the coefficients PR will be 0. And we applied your equation 12.5 and 12.6 with period that's equal to 4 to determine the remaining coefficients, which is only for a sub r, where from the second equality holds because the function is even in x. In solving for AR, we have this final answer here, which is equal to 16 over pi squared r squared times -1r. Now, since this expression for AR has r squared in its denominator, to evaluate A naught, we return to the original definition. So evaluating for A naught, we have this one here, where your A naught is equal to 8 over 3. 8 over 3. The final expression for f of x is then this function here. So you have your Fourier series for your x squared, that's equal to 4 over 3 plus 16 times the sum of -1 raised to the power of r over pi squared r squared cosine pi rx over 2. To have a review of this one, you can refer to the previous video for a thorough explanation of the solutions. It is sometimes possible to find the Fourier series of a function by integration or differentiation of another Fourier series. And this is what we're going to discuss in this section. If the Fourier series of f of x is integrated term by term, then the resulting Fourier series converges to the integral of f of x. If f of x is a continuous function of x for all x, and f of x is also periodic, then the Fourier series that results from the differentiating term by term converges to f prime of x, that provided that f prime of x itself satisfies the Dirichlet conditions. For example, let's find the Fourier series of f of x is equal to x cubed for 0 is less than x and less than or equal to 2. If you remember, in the previous example, we found the Fourier series for f of x is equal to x squared in the required range. And we have this answer here. Again, your x squared is equal to 4 over 3 plus 16 times the sum of -1r over pi squared r squared cosine pi rx over 2. So, if we integrate this term by term, this expression here, we can obtain this one here. So let's try to integrate this one. So for x squared, integrating your x squared. So we integrate this one, dx, and also this one for dx. So what we have is you have your x cubed over 3. This is equal to 4/3 x plus this is 32 times the sum of -1 r over pi squared or pi cubed r cubed sine, which is the integral of your cosine, sine pi rx over 2 plus c. So again, what we did was just to integrate the answer that we have in our previous example for your x squared, get an x cubed term, which is what we have here, where c is so far an arbitrary constant. Again, what we did to find for the what we are going to do to find for the Fourier series of f of x is equal to x cubed was we use the Fourier series that we have in our previous example, which is your Fourier series for your x squared. So we integrate this one and we have this expression here. But of course, we're not yet done because of this x term here. Again, we have not yet found the Fourier series for your x cubed because the term 4/3 x appears in the expansion, and we do not want this x squared here to appear in your series. By now differentiating the same initial expression for x squared, we obtain the following. So using the same expression for your x squared, the next thing that we can do is to differentiate this one in order to get an expression just for your x. So the derivative of your x squared is 2x. The derivative of your 4/3 is 0, since this is a constant, plus the derivative of this one in terms of x is you have the derivative of your cosine by our x over 2, which is negative sine by our x over 2 times the derivative of this expression here. So we have negative 8 times the sum of negative 1 r over pi r sine pi r x over 2. So if you're going to get the derivative of this one, this term here, you have pi r over 2, which you're going to multiply here. So you have 16 over 2, that's 8, and then pi r divided by pi squared r squared. So you just have your pi r. So that is what happened here. Now you now have an expression for your x. So what you can do here is you can actually divide both sides by 2. So dividing this one by 2, both sides, you can get just an expression for your x. And this expression for your x is what we're going to use in this term here. So we can now write the full Fourier expansion of your x cubed as the following. So this one, this is your this is your 4/3 x, okay, and this one is just what we got earlier. So your x cubed is equal to negative 16 times this expression here plus 19 times the sum of this expression here. So this is your Fourier expansion of your x cubed. And finally, we can find the constant c by considering your f of 0. And at x equals 0, our Fourier expansion just gives us your x cubed is equal to c. Because this will become 0, this will also become 0. So you just have your x cubed is equal to c. Since all the sign terms are 0, hence your c is just equal to 0 because the only way for the for this one to be true is when your c is equal to 0. So in summary, what we did here was, in order to find for the Fourier series for x cubed, we just use the previous Fourier expansion that we got for your x squared. So what we did first was to integrate, and then we have your x cubed term. However, we were still not able to write the complete Fourier expansion because of your 4/3 x, and we do not want that one in our expansion. So what we did is using the same expansion for your x squared, we differentiated term by term, and then finally we were able to write the full Fourier expansion of your x cubed. Now let's discuss your complex Fourier series. As a Fourier series expansion in general contains both sine and cosine parts, it may be written more compactly using a complex exponential expansion. So here we are going to use the lessons that you have obtained in your uh, in your complex numbers. This simplification makes use of the property that the exponential of IRx is equal to cosine Rx plus I sine Rx. The complex Fourier series expansion is then written as your f of x is equal to the sum of your CR exponential of 2 pi I Rx over L from R is equal to negative infinity to positive infinity. So this one here is your Fourier series in terms of your complex exponential expansion. The Fourier coefficients are given by the following. So the Fourier coefficient that we need to find is your CR. C sub r is equal to 1 over L times the integral of f of x exponential negative 2 pi r x over L dx integrated from x naught to x naught plus L. And this relation for your Fourier coefficient CR can be derived by multiplying your equation 12.9, which you have seen earlier, by the exponential of negative 2 pi I px over L before integrating and using the following orthogonality relation. So this is just the same process as we did in finding your AR and BR. The complex Fourier coefficients in 12.9 have the following relations with the real Fourier coefficients. Your C sub r is equal to 1/2 times AR minus IBR, and your C sub minus R is equal to 1/2 AR plus IBR. Note that if f of x is real, then your C minus R is equal to CR star, where the asterisk represents the complex conjugation. So this one here is the relationship of your uh, complex Fourier coefficient CR to your real Fourier coefficients AR and BR. For example, let's find a complex Fourier series for f of x that's equal to x in the range of negative 2 less than x less than 2. So we start with your complex Fourier constant CR, where your CR is equal to 1 over L times the integral of f of x exponential negative 2 pi I Rx over L dx, integrated from x naught to x naught plus L. And for R that is not equal to 0, so you have 1 over 4 because your period here is from negative 2 to 2, so that means it makes your period 4. And then your f of x here is equal to x. So we just substitute here your x in the expression times the exponential of negative pi rx over 2, because you have 2 over 4 here, so you just have 1/2 dx. So the next step is integrating this one, and you already know how to integrate a term where you have your we have a term of the form x exponential x. Okay, so integrating this one, you have this term here, and solving further, you get this term here with a final form of 2i over pi r times negative 1 raised to r. So this is your Fourier series, complex Fourier series for f of x that's equal to x. So you can pause the video to carefully analyze the solution here, or you can also try it yourselves. Just for some tips, you can also use your integration table to find for the integral of integrals of this form here. And for r that's equal to 0, we find that your c sub 0 is equal to 0. And hence, using again your complex Fourier series, Replacing your CR with this value here, you get your complex Fourier series for your x that's equal to the sum of 2i negative 1 raised to the power of r over r pi times the exponential of pi I rx over 2. So this one here is your complex Fourier series for your f of x, which is equal to x.